Okay, well, welcome to today's lecture and brief lab demo on dynamic light scattering. So this instrumentation module is going to talk a little bit about how the system works, and then I'm going to briefly show you the instrument and the software. But then there's going to be a fairly extensive module where you use the instrument remotely while we change some samples out for you. Okay, so this is going to be, fortunately, one of those opportunities for you to actually use an instrument, which I'm really excited about. We've never had this instrument in the teaching lab series before, and so this was a good collaborative effort among the faculty to get this instrument. It's about $50,000, so we're really happy. And I hate it that you can't actually use it in person, but I think this is a good next best thing. Okay, so what we're going to talk today about is dynamic light scattering. And so the dynamic means that we're going to look at how does this light scatter over time, okay? The rest should be pretty self-explanatory. You might also hear this called photon correlation spectroscopy. And we'll spend quite a bit on the correlation when I talk about this a little bit more. But these are the exact same techniques, okay? Dynamic light scattering. So what are the two main things that you get? Well, the first one is nanoparticle size, okay? The second one is nanoparticle charge. This is also called the zeta potential. Okay? So you might think, well, I mean, I can use electron microscopy, I can use AFM, like there's lots of ways to get a nanoparticle size, right? So why would I want to use this technique? Well, why, or the advantages. The first is that it's just really easy, right? This has been around for about 30 years. It's really easy to put your sample in a cuvette, drop it in the instrument, and hit play, right? This isn't like electron microscopy or AFM where you need months or years of training to become pretty good at it. The second one is that it's non-destructive. And that can be key, especially in nano, right? Because maybe you have a very precious sample, a sample you don't want to have ruined. And when you put your sample in the electron microscope, you're not getting it back, right? Because it's going to be dried, it's going to be on this grid. So it's the end of that sample. But in dynamic light scattering, you can take your sample, put it in the instrument, then take it back out, put it in your pocket, take it home, never let it out of your sight, right? It's non-destructive. The third one is that it's pretty fast, right? So within 3 minutes, you can know with pretty good accuracy the size of your particles and how monodisperse or polydisperse are your samples. And that, you just can't do that with electron microscopy, right? It's also pretty cheap. So like I said, $50,000, which compared to an electron microscope is pretty affordable. And 5, believe it or not, it's actually pretty rugged. I've used systems like this that are 15 years old, and they're still going pretty great. Okay. One thing that we'll see later is that we're measuring both of these are intrinsic properties. intrinsic properties, and this is in contrast to an extrinsic property. So an intrinsic property is going to be independent of the amount of the material that you have. Okay? Independent of concentration. So this would be something like density, right? Density of water is the same whether you have a gallon of water or a milliliter of water, right? The density is 1 gram per centimeter squared, right? Whereas the weight would be an extrinsic property, okay? So the average size of your particles is the same whether you have 100 or 100,000 particles, right? The average should be the same unless you're at really, really low particle counts, in which this wouldn't even work. Similarly, the charge is an intrinsic property, right? So the average surface charge on your particles is going to be the same whether you have 100 or 100 million, okay? So what makes this nice is that it's relatively, this technique is relatively insensitive to the concentration of your sample, which is nice when you have a low sample volume or a low sample concentration, okay? So let's talk a little bit about how the instrument is designed. So the first thing we have is our source. So in this case, unlike in absorption spectroscopy, we definitely use a laser, okay? This is generally a 532 nanometer laser. And we want it to be a laser because we want collimated light. Because collimated light is going to be scattered in a more uniform direction than non-coherent light. Okay, and that's what we're looking for is scatter. So this is actually a pretty key metric, right? So hopefully you learned in your other classes that a nanoparticle tends to scatter the most at wavelengths similar to its size, right? So a 532 nanometer laser is going to scatter the most, or excuse me, like 532 nanometer particles are going to scatter 532 nanometer light the most, okay? When you get farther and farther away from this, it's going to scatter less. Now that is not, an important corollary to that is that bigger particles always scatter more, right? But so like a 600 nanometer particle is always going to scatter more than a 10 nanometer particle, but it's going to scatter the most at 600 nanometers, okay? So this is kind of a consideration in terms of how do you make these systems sensitive to a wide range of particles, right? And so this is going to be one of the discussion questions is a thought experiment about how would you make your system sensitive to a wider range of particles and increase your sensitivity, okay? So the hint is that it's going to be in this area, okay? But the one we're going to use today is 532. 532 is cheap. It's common. It's right in the middle of the spectra, so we're going to pick up blue and red scattering as well. So that's a good region to work in. So here's our source, and then this is our sample. Yet again. So we're not going to work at directly 180. We're going to work at some angle, theta, to have our detector. And the detector here again is going to be a photodiode. If you've seen my lecture on absorption spectroscopy, you know how a photodiode works, is that it has a region of positive charge and a region of negative charge. That are coupled together. And when a photon comes in, it creates an electron and a hole. And that electron and a hole move to their respective regions, and you get current flowing. Okay? So that's how light in equals electricity out. Okay? So that's how our detector works. The reason we don't want this at 180 degrees is because we don't want all of this other incident light shining right at our detector, right? Because that signal or that light from the laser is going to swamp out all of the other scattered light, which we're actually interested in, and that has the information that we're interested in. So what this is going to give us then is photons per unit time. Okay? This then goes to, I'm just going to call it a correlator. So it's some software that we'll talk about in detail in a minute. But this is kind of where the magic happens, is this correlation. And so I'm just going to wave over it for now because it's coming. And then some kind of PC for readout. Okay? So that's how the system's kind of designed. So let's now talk a little bit about what's happening in our sample. DLS is based on Brownian motion. So the people who first discovered this were actually studying things like pollen, and that's how Brownian motion was first identified. So what is it? If we think about this being our nanoparticle, and these little x's, x equals the solvent. And right, I mean, nanoparticle doesn't have to be nanoparticle. It could be a grain of pollen. But these solvent molecules have entropy. They have thermal movement. They have thermal energy. And so they are in equilibrium with each other. They're in equilibrium with the solvent molecules that are even farther away. They're in equilibrium with the other particles closer. So there's some entropy here. And so there is a likelihood that more solvent can move to one side, right? There's also a likelihood that more solvent can move to the other side. So if there's more solvent on this side, you're more likely to have a movement in one direction or the other based on how the solvent is arranged. Okay? So this is kind of the essence of where this Brownian motion comes from, is this interaction of the particle with the solvent. Okay? So what do you think affects this? I already hinted at one is the temperature. Right? So more temperature in the system is going to generally produce more movement. Okay? The other big one is the size of the nanoparticle. A smaller particle is simply free to do more movement, right? It's going to be more susceptible to interactions with the solvent, and it can move faster, okay? Affected by temperature, size of nanoparticle, and the viscosity of the solvent, right? So if this stuff is, if the solvent's really sticky, if it's really gooey, it's less likely to have this rearrangement, it's less likely to have this impact on the particle movement. Okay? So increased temperature increased movement. That makes sense? Increased size, bigger particle, decreased movement. Increased viscosity, I think it's usually shown as this symbol. New, I think that's new. Haven't said my Greek alphabet in a long time. Increased viscosity, decreased movement of the nanoparticle. Right? Okay. Let's see. Another big consideration is that Brownian motion is only for colloidally stable particles. Right? Because we want the only, well, not the only, but the primary force of driving this is to be the interaction of the solvent with the particles, right? If we have something like gravity affecting our particles, sad face. If gravity is affecting your particles, that means they're falling out of solution. You've got a big tube of junk. Welcome to nanoengineering. Okay? That means gravity is affecting your particles, and therefore this movement is no longer true Brownian motion, right? Similarly, if you have particle-particle interactions, nanoparticle-nanoparticle interactions, it's no longer Brownian motion, right? Because this is a different force interacting on your, driving the particle movement, right? So let me show you a video, a very short video of what Brownian motion looks like. So this is a dark field microscope, and hopefully these are just silver nanoparticles that are moving underneath a dark field microscope. Isn't that amazing? I mean, this is what these particles look like. We have an instrument, the instrument that we're using today, dynamic light scattering, does not do this, right? You're not going to image these particles like this. But it's using this same principle. This is what Brownian motion looks like. And if you have a dark field microscope or another nanoparticle tracking analysis system, this is the kind of data you can get. So I always feel like these are such fun images because, I don't know, look how perky our nanoparticles are. Okay? So now let me show you another video of different sizes. Look at this particle here that's 800, this particle here that's 50, and this particle here at 240. So this is a mixture of different particles. train your eye on how much this is moving versus how much this one's moving, right? Versus how much this one's moving. The bigger particle is moving a lot less than that smaller particle. Okay, so this is an experiment where people took 3 different known sizes and mixed them together. So the other thing you'll notice is look how much more these bigger particles are scattering relative to this small particle, right? There's an intensity effect. So there's the overall intensity difference and the amount of movement. So we actually have this instrument down in the basement. And it's a whole other story, but this, I think, really nicely illustrates some of the principles that we're using in dynamic light scattering. Again, this is Brownian motion. Okay? Okay, so more specifically, we can discuss this as so here K is the Boltzmann constant. T is temperature. 3 pi is 3 pi. Nu is our viscosity. D is our diffusion coefficient. So what do we mean by this, the diffusion coefficient? Well, it's simply how likely is that nanoparticle to move, right? Is it going to be like that little particle that we showed earlier that was going crazy, or is it going to be more like that small one that was just sort of hovering, right? Big diffusion coefficient, small diffusion coefficient. Okay? And then little dh is our hydrodynamic diameter. You'll probably hear me say hydrodynamic radius, same thing, except that becomes a 6. Right? Okay, so we know this. We can measure this, or we know it. We know this because we know what our solvent is. This is what we're going to measure. And this is what we calculate. So this is our nanoparticle size. But notice that I'm not saying size, right? I'm clearly saying hydrodynamic diameter. So what do we mean by that? Maybe let's go here. It's a hard sphere that diffuses at the same speed as the species being measured. So what does that mean? If we think about a nanoparticle, it's not really just that nanoparticle, right? Because you know that this has a stern layer, it has an electrical double layer, it has association with the solvent, right? We just talked about this solvent layer, right? So the hard sphere that diffuses at the same speed as the species being measured is actually, let me use a different color just because I can. So this green dashed is the hydrodynamic radius, right? And so it's going to be affected by your solvent quite a bit, right? It's going to be affected by the pH. It's going to be affected by the ionic strength. So choosing your solvent in DLS is important. What's another example of a hydrodynamic diameter? Say you had a cluster of 4 nanoparticles and this associated solvent. So now your hydrodynamic radius is going to be about the same size as this system, even though you have actually 4 smaller particles. Not colloidally stable, sticking together, sad face. What if you have something that looks like this? A two-dimensional system, a nanorod, and of course it has solvent. The hydrodynamic radius of this is still going to look something like this, a hard sphere that diffuses at the same speed as the species being measured. Okay? So this is kind of a key consideration. This technique does not do very well with non-spherical systems. Okay? So if we think a little bit more about a particle that has salt, positive, negative, positive, negative. So what do you think happens when we have ionic strength and size? So if we have more salt in solution, what does that do to the hydrodynamic radius? It actually decreases it because your Debye length is getting smaller because you have simply more salts to associate with each other, right? When you have more charge, you have more charge to interact with other charge rather than with the nanoparticle. So therefore, the amount of charge that is actually associated with the particle goes down when you have a higher ionic strength. Okay? And therefore, higher ionic strength, lower hydrodynamic radius, lower Debye length. Is that how you spell Debye? Yes. Lower Debye length. So picking your salt concentration is kind of important. Okay? This is why, you know, a lot of particles don't do well in salts, right? If there's so much salts, the solvent loses interest in holding on to the particle, right? And therefore, the particles are more interested in holding on to each other. Falling out of solution, sad face. Okay, so this is some of the mechanics that is underlying this. I'm going to save this for now. Okay. So we have our particles. We have them in solution. We put them in our cuvette, shine a laser on them, and monitor the scatter. So what the instrument first measures is intensity. I mean, it's really, like I said earlier, it's counting photons per second, right? And what it initially does is measure that at a very short time frame, right? And if we have a small particle, like I showed you on that video, you're going to have a wide variation in intensity and relatively fast movement, right? And if we have a large particle, and look at intensity versus time, you're going to have less movement and less erratic movement. Erratic's probably not a good word, but slower movement, right? Slower diffusion. So the rate of fluctuation is what is proportional to size. Right? So don't look so much at the magnitude. What you're kind of looking at is this. And see how you just kind of have more narrow peaks here on your small than your large. Okay. This is actually the first step. Now, what you're going to do is you're going to keep collecting this nanosecond scale spectra again over many seconds. Okay? So when we do this on the order of seconds versus a nanosecond capture, like if this is, I don't know, 50 nanoseconds, and then I do this experiment for 30 seconds, that's 10 orders of magnitude, right? 9 orders of magnitude. Okay? So this is kind of a long time, or a very short amount of time compared to the measurement time. Okay. So what I'm going to do next is I'm going to repeat this again. I'm going to maybe wait a second, and then I'm going to repeat this nanosecond measurement. And I'm going to look at intensity versus time. Repeat the exact same thing. Okay. What I want you to try to appreciate is that this larger particle looks pretty similar to baseline. That's what I'm trying to draw here. Because it's a smaller particle, or excuse me, it's a bigger particle, and it hasn't had as much time to diffuse. It hasn't had as, it requires more time to move. The rate of fluctuation is proportional to size. Meanwhile, this small particle, like I showed you earlier, that's running around like crazy, it already has positioned itself differently. Okay? Let me actually explain a little bit more about how we're getting this. Let me do it over here. Imagine that you have two particles. Laser hits them. And they scatter, they're exact same particle size, and they scatter the same. And then imagine at time point 2, t equals 1, these particles have moved a little bit. This particle has moved relative to this one. So therefore, the scattering is different. So where here I have constructive interference, and here I have destructive interference. Right? So these are obviously the extreme cases, but this is what would cause this difference in intensity over time. That's why this green curve would be different relative to the black curve. Okay? Because you would have particles in different space, and therefore you would have a different, very short 50 nanosecond intensity spectrum. Okay? Unless your particles are really big and they still basically look like this anyway. And then the combination looks basically the same. Okay? Obviously, in reality, you have way more than two particles, right? You have billions of particles. But they all are collectively, constructively, and destructively interfering. Okay? So then, if we go to t equals 2, maybe now we're starting to see some difference in our larger one, but still relatively the same. But maybe here, on our smaller particle, we're much, much different. Because more time has elapsed, more time for the particles to rearrange, more time for a different intensity spectrum, if you will, to be collected. So what the instrument does for you then is it plots time, and now I'm plotting in seconds. This is a key point. Earlier I was plotting in nanoseconds. Now I'm plotting in seconds. And what am I going to plot? I'm going to plot the correlation. So remember earlier I said the correlator is a part of that block diagram. And so if these things were perfectly correlated, it would have a value of 1. And if they were perfectly uncorrelated, it would have a value of 0. And so what we're going to do is we're going to plot t equals 0, 0. I mean, this would be correlating, I guess, with itself, if you will. So there's more distance between these 2 points over here, right? This correlates less well. Green with black correlates less well with each other for the small particle than for the large particle, right? When you get to time point equals 2, there's very little correlation over here. Okay? So you get this, they're generally kind of an exponential thing, where this one comes down much quicker than this one. This is the raw data. This is actually all raw data. The first piece of data that you're going to see on the instrument takes the log transformation of this. Right, so it's going to be like 10 to the negative 5th seconds, 10 to the negative 4th, 10 to the negative 3, all the way up to, maybe it goes for 100 seconds, something like that. This is one of those parameters that you can change. And again, we're plotting this correlation. But the difference now is this is log. Okay? And what this is going to look like is something like that. I'm going to get rid of my little marks just for clarity. Okay, so is this the big or small particle then, the way I drew it? Well, what do we know? The first thing we know is that a big particle is going to correlate longer, right? So that's what a big particle would look like. Relative to a small particle. So this is a key metric, right? How long does our particle remain correlated? What about this? See how this does not perfectly interact with 1? What's that a function of? Well, you know, it's primarily the impact of noise. Let's call, okay, so let's call this region 1. length of time well correlated. So this region 1, this is region 1 right here, right? This metric, length of time well correlated. Longer equals bigger particle. This region right here, this offset, region number 2, offset from unity, that's a function of noise, and that's a function of primarily particle concentration, right? And if I have a really small particle concentration, right, I don't need to write this down. It just makes sense. If I have a small particle concentration, there's just not much light scattering, right? So therefore, there's not many photons that are hitting my detector. And if there's not many photons hitting my detector, my signal's low. Therefore, the impact of the noise of the detector becomes higher, right? So particle concentration too low. Also, particle concentration too high. So if my particle concentration is too high, what I start to get is what's known as multiple scattering, where the photon that scatters off of one particle is then bounced off yet another particle and another particle and another particle, and that not only, that quickly reduces my correlation, right? The correlation, even at baseline, is low, right? And that's why this offset from perfect correlation is low if I have too high of a concentration. Similarly, too low of a concentration, right? You could also have other things like absorbance, fluorescence. If you have absorbance or fluorescence, you're going to have extraneous photons hitting the detector, and therefore you have less of an offset from perfect correlation, even at baseline. Okay. So that's region 1, region 2. Let's talk about down here, region 3. 3 is baseline. At a very long time point, what do you expect this to be, regardless of the particle size? Right? At a very long time point, it should be 0, right? And it should stay at 0. Because there's no possible way that these are the 100 billion particles that you have in your system are going to ever go back to the black curve at t equals 0, right? But what you will sometimes see is that it will stay elevated it'll stay elevated and it'll wobble. And what that means, what do you think that means? Think about it for a hot minute. If you have background variation, whoop, that means that you've got dust in your sample. Or you've got some kind of aggregation. You've got an imperfect sample. Okay? And then the fourth region we'll talk about is, let's call this region 4. Same thing, time in seconds, log, correlation. What this is going to tell you about is how similar the particles are to each other. Right? If every particle was the same size, this rate of loss of correlation should be the same every time you replicate the measurement. But if you have a broad range of particles, you're going to have a broad range of these slopes. M of 1 does not equal M of 2, does not equal M of 3. This is polydisperse, which we generally think of as bad. So this just means that in this situation, you have one particle like this, one particle like this, one particle like this, one particle like this. They're different sizes. As opposed to a monodisperse, system that looks like this. Okay? So that's why, you know, we also, like I said, people also call this photon correlation spectroscopy. I used this technique for years without really understanding this. And so, and it's because the instrument always showed me this, and I was like, whatever, 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 just tell me the size. But it's actually really useful to understand this. Okay? Now, we still haven't gotten to size, right? So how do we use this data to determine what size it is? Well, we're going to use this other equation. Okay. So here, B is the baseline at long time, meaning 10 to the second seconds. A is the amplitude or the intercept. So B is my baseline, this tangent line. Right? That's my B is baseline, and there's A is my intercept. Q is my scattering vector. I'm going to skip that. Do that in a graduate class. N is the refractive index. Oh, I'm sorry, this was, yeah, new. Okay, let's just write it. The scattering vector is 4 pi this is our scattering vector, 4 pi refractive index over my wavelength at the angle with which I'm scattering. Theta is my detection angle. And then finally, I get to D, which is my diffusion coefficient. This is my correlation delay time. Where am I on here? And that's why this is the summation of all of these different events. Okay? Baseline remains constant. Amplitude remains constant. And then I have these multiple events at different correlation times. Correlation time 1, correlation time 2. Okay? So, I know this, I know this, I know this, I know this. I use these to calculate my scattering vector. I can measure this, measure, and I can measure this. So therefore, I can calculate my diffusion coefficient. Aha! Diffusion coefficient was the last thing we needed here in our Stokes-Einstein equation. I don't know if I told you this. This is called Stokes-Einstein. The Stokes-Einstein equation. I have measured my diffusion coefficient using correlation techniques. I know the viscosity, I know the temperature, I know Boltzmann's constant, and therefore I can calculate my hydrodynamic radius. So what the instrument's going to give you, it's going to give you a metric called the Z average and the PDI. This is polydispersity index. And so this goes from 0 to 1, where 0, every particle is exactly the same. 1, every particle is different. Generally, if it's less than 0.03, that's okay. If it's less than 0.01, that's pretty happy. Less than 0.01 is wow, right? So this is kind of the range of numbers you're going to get. And then the Z average is basically the mean particle size based on scattering. Okay? Z average, it's the intensity weighted mean diameter. Meaning that if you use intensity to measure size, it's that value in the middle. So the instrument actually will give you several kinds of ways of showing the data. So one is this intensity weighted. So it's kind of a weird way of thinking about this, okay? You're using the raw scattering intensity through the process that I walked you through to estimate the size. The only problem is that it's going to be, it's weighted to bigger particles. It's weighted. It's weighted to heavier particles because bigger particles scatter more. So the size that you get here in nanometers, if you have some big chunks in there, the number can be off because those bigger particles are having a bigger impact on the overall Z average number. So the software, if you know what do you need to know? The particle optical properties. If you know the particle properties, such as the refractive index and the absorbance, it uses me theory to give you a volume or a number in addition to intensity. So I'm not going to walk you through all of this. It's actually a little bit proprietary. But if you had a situation where you took 60 nanometer particles and 220 at 1% by weight, at 1% by weight, and you mix these two together, okay? So think about this. If I had 10 microliters of each of these, which one's going to, and they're both 1% by weight, which one's going to have more particles? The 60 nanometer one, right? Because there's each one weighs less, and therefore you're going to need more overall particles to have one weight percent. Okay? So if we had this sample, we mixed them 1-to-1, right? For each big one, there's one small one. If you tell the software, okay, show me the volume, it would look like this. 50, 50. But if you said, show me the intensity, it's going to be almost 10 to 90. Because these smaller particles are going to be scattering a lot more. But if you said, show me the number, it's going to be like 98 to 2, because you have a lot more of the smaller particles. Okay? So this is true. It's all relative to each other. And which one of these is the best one for your measurement? I don't know is the right answer. In the exercise we're going to have you do, you'll look at a couple different, you'll look at all three of these and understand some of the differences that happen when you present the same data, right? Because this all came from the same correlation, correlogram, the same correlation data. It's just presented differently. And I'm doing a little bit of hand waving here in terms of how they get this intensity data into volume data. But they're using basically the refractive index and the absorbance to know how does that intensity of the scatter at a given size correlate to the volume of the particle or the number of particles that should be there. Okay? So this is an introduction to DLS. What's going to be coming up is we're going to look at the instrument relatively briefly, and we'll also have another lecture about using the same concepts of dynamic light scattering and correlation spectroscopy, but to use it to measure particle charge, right? Because I told you at the very beginning, DLS does the two main things that we're going to use it for is size and charge. So we still haven't talked about how to do charge, and we still haven't actually looked at the instrument. Those will be coming up. Okay? Okay, so this is my the second part of a lecture on dynamic light scattering. And so you just saw a lot of content about how we can use DLS to measure size, right? And what I want to talk to you now about is how we can use it to measure charge, okay? And so what exactly do we mean by the charge? Well, you've probably seen this in class where if you have a nanoparticle and you have the stern layer, the very tightly bound inner layer, and then you have the electrical double layer. Electrical double layer. Charge, or what we're going to call zeta potential. Let's call it this little symbol. Zeta potential is the voltage at the double layer. So what is my potential across this double layer, right? Are there more positive or negative charges across that double layer? So why do we care about it? The primary reason we care about it is that it governs particle stability. That's thing one, I guess. Why? One is particle stability. So it's an indicator of how stable your particle will be. So what do you think? Like, are positive particles more stable than negative? More stable than neutral? So it turns out that particle stability is really a function here in terms of the overall absolute value of the charge. And hopefully that makes sense, that if you have two really negative particles, they're going to really repulse, right? And if we have two really positive particles, they're going to repulse, right? It's pretty unlikely that you very often make a solution of positive and negatively charged particles, right? Generally, all of your particles are going to have the same charge, right? So a good rule of thumb if this is 0 millivolts to positive 60 millivolts and negative 60 millivolts, this region around 0, like roughly plus or minus 10 millivolts, that's pretty bad. That has pretty poor colloidal stability. Poor colloidal stability, right? Because at this point, there's relatively little charge repulsing these particles. But if we get out here, maybe 20 or so, I don't think I've ever measured anything that's like more than 50. I guess it exists. This is good, smiley face. A good here, say, let's call it 20 millivolts to 50 millivolts, smiley face. That's negative 20, right? So these are good regions to be in, okay? So that's thing one, is it's kind of a rough metric of how stable is my particle going to be on the shelf, right? Can I leave it for a couple weeks, couple days, couple years? The other value that really comes with zeta is in monitoring a reaction step. So monitoring a reaction step. So say that you start, with a classic example, you've got a nanoparticle and it has some kind of small molecule on the surface. So maybe it's C-tab, you're making a gold nanorod. Maybe it's sodium citrate, you're making a gold sphere. So there's some kind of charge, small, right? And then say you want to put a polymer on it. So we put like polyethylene glycol. So how are you going to prove to anybody that you've actually put PEG on your particle, right? You say, okay, I took my gold particles, I added some polyethylene glycol, I shook it up, I let it react overnight, then I spun the particles down, washed the pellet, spun them down again, right? So that's a tough measurement to make. You're going to put this in the electron microscope? That's not going to work. I mean, do you think polyethylene glycol has much electron density? It's carbon and oxygen repeating. Does that have much electron density? No. So you can't really do electron microscopy. It's kind of tough, but it's really easy with zeta potential, because what you can do is look at intensity and charge in millivolts. And so if your original particle, let's say your gold is, I don't know, 50 millivolts plus 50 millivolts. After you put PEG on it, it's probably going to be 30 millivolts or something to that effect, right? What else could you do? I mean, you could also do the exact same thing that I talked about with size, is you could also look at size, intensity, and here, this is bare, and this is going to be PEG. So here, PEG is going to slightly decrease your charge, right? So that's another really area of supreme value that measuring the zeta potential has. Okay, so what are some practical considerations? I mean, the solvent makes a big difference, right? And in particular, the pH of the solvent and the ionic strength. Perhaps the biggest two, okay? So you can look at the pH. You can monitor this as a function of pH. And as you have more and more and more protons, it should be more positive. And there's some point called the isoelectric point where your particles are neutral. And so this is not a very common experiment, but it will tell you what range of pHs your particles are stable in, right? You would probably want to avoid kind of that range, right? Your particles may aggregate it for higher or lower pHs for other reasons. So we talked about the effect of ionic strength when we talked about size, but we can think about it here again. So if we add more and more and more and more and more charge, there's going to be less and less and less and less affinity of that charge for the surface of the nanoparticle, right? So as we increase ionic strength, we're going to decrease the double layer, right? And we talked about how that will give us a smaller size, or at least a smaller hydrodynamic radius in the size characterization. Okay? But it can also dramatically affect the zeta potential. Okay, so really, and what is the right answer? The reality is there isn't, right? So what the reality that you have to do is when you report a zeta value, you have to report it zeta potential value at a given pH and ionic strength, right? Because the surface charge, the potential across the double layer, changes with both of these conditions, right? So it's not as if there's like, the right condition to measure this. But you have to report it, the value you're interested in needs to be at the conditions you're interested in. Okay? So how do we make this measurement practically? Well, again, it's going to be very similar to what I showed you before, where we're going to look at the correlation, where this was the correlation, and this is time, and we're going to watch it decay. The main difference is we're going to perturb the system. And so we're going to have this little capillary. This is what the sample looks like. And one end is positive and one end is negative. And we're going to artificially induce some movement. So remember, when we were doing size, we were only looking at Brownian motion. And here we're going to look at electrophoresis. I'm going to show you. So the cuvette for the sizing looks like this. And so, just a standard cuvette. And here is the cuvette for zeta potential. And so it's focusing on my face. So there you can see it's kind of like this. There it is, it didn't focus. It has these two little tubes at the top where you put in the sample. And then it literally is, you're just going to put potential across these two electrodes. We'll get a better image of it here. But this is what I'm representing. It's this little capillary that has a port in and a port out. And then we're going to put potential across it. Our particles are in here, and we're going to watch their movement, okay? And we're going to look at how does their velocity change as a function of field. Okay? And we're going to use this correlation spectroscopy to monitor that velocity, and we're going to artificially perturb the field. And the slope of this line is what's known as electrophoretic mobility. Right? So how mobile are these species in this field? Okay? And so then we're going to use the Henry equation zeta potential. So that's going to come from our slope. Our O'Flynn epsilon is the dielectric. Viscosity. What else is up there? This term. This is a separate function, which I'm definitely not. Henry's function, which I'm not going to talk about. So we know the dielectric constant, we know the viscosity, we can get this from a textbook, and we're going to measure the electrophoretic mobility, and so that's how we back calculate the zeta potential. Okay? So practically, this is still an intrinsic property. It still is a function of, it's independent of the mass of the particles that we have. It's still a pretty robust routine measurement. And so now we're going to go over to the instrument, and I'll show you how to make a couple measurements in a very kind of overviewed way. And then you'll get a more detailed protocol when you dial into the instrument and start to use it. OK, so we've prepared a sample for the system. These are polystyrene latex beads, so they should be pretty monodispersed, pretty same size, and they also have a pretty well calibrated surface charge. So I can show you the instrument in a little more detail. I mean, not that there's a lot to see. This is what the instrument looks like. If I turn it a little bit, you can see where the sample goes. So this is probably the most black boxy instrument that we have this year. And the reason it's so black boxy is because the technology has just been it's pretty matured. And so any control that you need to do is going to be done with the software. So it really is as simple as we're going to put the cuvette in and close this. And then I'm going to come over here. When you dial into the instrument, you're going to use this software a little bit more. But I'm just going to go ahead and hit play up here and call this, and hit OK. And so you can see this. I'm going to hit start. And so you can see this is our background down here. Remember, each point on the correlation is roughly 50 nanoseconds. What it's first doing now, it's equilibrating, because we talked about how important temperature was in these measurements, right? And so first it needs to at least stabilize the temperature and measure the temperature. Now it's going to optimize measurement settings, so that's probably the photodiode. It's going to set the proper gain across the photodiode, and then it's going to take these measurements. And so this is all replicates, so it's going to do 12 runs of 3 replicates each, which is probably overkill. Well, I'm not going to have you do this. But you can immediately, see how quick that was? I immediately am getting this number weighted. Remember we talked about the differences, intensity, volume, and number weighted. It's showing us the number, and it's showing us the hydrodynamic radius. And then if we look up here, it's showing the Z average size, the polydispersity index, which I told you 0.000, below 0.01 is wow. So these are very monodispersed particles, and it's showing us where the peak is. So the height of this peak is about 295, and the Z average is about 314. So that kind of makes sense, right? Because we said that it's the bigger particles are going to bias because the bigger particles scatter more. Okay? So, but let's back out of here. And if we come over here, no data yet. Run 9 of 12. These are counts. Let it go for 12 measurements. So I guess it's going to do 3 runs of 12. So 36 altogether. So let's let it finish this, and then we can probably see the correlation spectroscopy. Oh, and here's our intensity. Our intensity number. I told you we have number and intensity. Okay, so now it finished that. So I think I can close this window and come up here to my raw correlation data. Okay, so here is my correlation coefficient, and here is time in microseconds. So 1,000 microseconds, 10,000, I guess that's 100,000 microseconds, if not a million. And so the baseline, remember the 4 points that we looked here, right? The first one was our intercept. So it's intercepting close to 0.9. So that means that the signal to noise ratio is pretty good. Then we look at the width where it remains flat. And so that is what governs our size. Notice, look how fast this drops off. This is a really fast drop off. And that suggests that it's a monodispersed particle. Okay? And then the last one is the baseline. And the baseline kind of goes to 0 and stays to 0, which suggests that the solvent itself is pretty pure and that the particles are not aggregating. There's no new particles due to sedimentation. So this is your raw correlation data. And then you can look at here's the intensity, the percentage. Here's the volume view. And can we show the number view? We may not be able to show the number view right here, but on your report, I think I will be able to have you look at the number view, unless it's... Do you know where it is, Wanju? Yes. Where is it? Right click.
And then you can change it. Size, intensity.
Size, intensity.
Number.
Size, intensity, number.
Yes.
Apply.
Yes.
Oh, nice. So now I'm putting them, now I changed it to number, and here my second read has been done. Okay. So when I lectured earlier, I showed you 2 peaks, and we don't have two particles in here. It's only one particle type. So intensity is probably pretty close to number, which is probably pretty close to volume. Okay. So that's just a quick overview. I'm not going to walk you through step by step of the software, but the protocol that we give you is going to walk you through that. But what you can appreciate, I'm really glad that you can see this raw data. And so we'll also include a bad particle whenever you do this from home. So let's pause the video, and then we'll go on to Zeta. Okay, so now we're going to move on to a Zeta potential measurement. And so here's the sample holder that we talked about earlier. So you can appreciate, again, it's this little U-shaped, and then you can also appreciate that it has these electrodes on either side. And you can then see when you go into the instrument that it does have the coupling where it couples with those electrodes to put potential across. So that just is seated down there properly. Actually, there's, yeah. Okay. So now, again, you'll get a protocol with the software, but I'm just going to go ahead and hit play. And we can just hit OK. And so insert cell, press play when ready. So one drawback of this model, I would say, is that you do have to change the samples out manually. So sometimes we'll want to look at maybe 30 samples in a day. And so it's not like the plate reader upstairs where we had 96 individual wells and each well can just be set up in advance. But other than that, I've been pretty happy with this instrument. So there, just that fast, I'm getting a measurement of about negative 28 millivolts with a standard deviation of about 10. Okay, so it's going to start on its second of 3 measurements, and I can come over here and look at the phase plot, which is analogous. It's a processed version of the correlation spectroscopy. I can look at my overall zeta potential, and let's see, voltage and current. I can look at how does voltage change with time when these different currents are, how do current and voltage change with time? Okay. This is the main number, of course, that most people are looking for, is this zeta potential measurement. Okay. So quick and easy. So I'm hoping this is going to be quick and easy for you as you dial into this instrument. Someone is going to be here changing out the samples. So it's either going to be via Zoom or via a text message or something when you say, okay, switch the sample. And either me or one of the TAs will switch the sample over. But I hope this is a good experience for you, and I think it's a good learning opportunity.